So, right. So I'm fairly sure that you already know what STIR is, but I will briefly summarize it here. So it is a C++ open source library. Um, Primarily, it's focused in PET image reconstruction, but it can do so many things, like Spect image reconstruction, a lot of image analysis, and supports multiple scanners. It has Python and MATLAB interfaces, and is the main engine behind SIRF, synergistic image reconstruction framework. There have been plenty of meetings, all of them around the IEEE conference, and now we are in Tampa. And as you see, we have also two virtual ones in 21 and 2022. This year's program has 6 presenters, and you can find them here in the slide. It's read over there. But also we have other works that use STIR, and they are very interesting posters and presentations, and I think that you should definitely keep an eye for them. And also would like to acknowledge our dinner comes from the EPSRC CCP SINERB project, courtesy of Thielemans. And we would like to thank all the organizers of the IEEE committee, and especially Ralph Engels for all the emails that we bounced on him, and he is very happy to reply to us. And without any further ado, I would like to invite our first presenter, which is, I can't read it from Sam. All right, Sam, please.
Thank you. Is there that clicky thing? Was that disappeared? There definitely was one when we were here earlier. Maybe it's hidden itself. Okay.
Yeah. That is.
Oh, yeah. Cool. Okay. Hi, my name's Sam Porter. I'm a PhD student with UCL and MPL in the UK. And today I'm going to present a presentation in kind of 2 parts. So firstly, some work that I've been doing on a SIMIND-SIRF integration program, so an API fully with Python, which I presented kind of some really early stuff at the Vancouver STIR user group last year. Completely changed the way it works. And then secondly, present a use case where using this connection for reconstruction using something called a residual correction, which I'll explain a bit later. So firstly, I'll go over the basic structure of the connection code, and then some just preliminary results using this connection just to simulate some forward projections. And then talk about this, the basic idea behind what the residual correction method is, and some really preliminary results that we've had using that. So I've been trying to make the connection as simple as possible. So at the moment, you just input a file path to a SIMIND-config file, so .smc file, a source image data from SIRF, source an attenuation map, image data object from SIRF, and a template acquisition data object. And you instantiate a SIMIND simulator object. And this will create a simulation config object based on this SIMIND configuration file that you give it. And from there, you can change all the configurations, so all the different indexes, they're called in SIMIND. So that's the collimator, the crystal size, and so on. And then run a simulation, and then this will save an output configuration file, and you should be able to get SIRF projections, Monte Carlo simulations out on the other side. So some quick syntax. So creating the simulator object at the top there, giving it a file path and some SIRF objects. And this creates a simulation config object as a property of that SIMIND simulator object. And then you can add comments to your output file, change index values like this, change flags, so setting different things like attenuation on and off, set text variables. So this is collimators and stuff that SIMIND has already ready within the program, and also add different energy windows and runtime switches, such as how accurate you want the simulation to be. And then from this, you can print the configuration so you can see all of your configurations for that simulation within Python. And if anyone has used SIMIND before, this can be very complicated using the current in the current way that SIMIND works. Then you can run the simulation, and this will save a new config file so that you have some evidence of what you've used in your simulation, and then using this functionality here to get SIRF objects straight out of the simulation. So these are some quick results using SIMIND. So we've used a smooth OSCM reconstruction as a source file, and this doesn't model any septal penetration. It's lutetium-177, and this simulation takes 36 minutes, so it's quite quick. And here we've compared, so the SIMIND total output, so that's prompts and scatter, compared this to measured data, and then plotted the scatter as well, and then the trues, which is the total minus the scatter. You see that everything's pretty accurate. Seems like SIMIND does slightly overestimate scatter, but that might just be the true scatter. And so a similar thing for yttrium-90. So this takes a lot longer because septal penetration is modeled here. So this takes about 7 hours. And again, we've compared this to the measured data. So for the reason that I wanted to do this connection was to do reconstructions with a SIMIND Monte Carlo within a SIRF reconstruction program. So I've been using this residual correction method, which was originally created in 2010 to account for positron range in PET. And basically what you do is you do a reconstruction with an estimated additive, with an additive estimate. And then you, after this reconstruction, you do a forward projection with an accurate Monte Carlo forward projection and a forward projection with your fast forward projection using STIR in this case. And then you look at the differences between that accurate forward projection and the fast forward projection, and you add this to the additive estimate, and then you do another reconstruction, update your additive estimate with the residual correction again, and so on. And so previously SIMIND has been used as a forward projector, but it's very slow if you use it every single time. And so what we're trying to do here is trying to get the same accuracy as using an accurate Monte Carlo forward projection, but much faster. And so initially we did a quick kind of feasibility test. So this was with yttrium-90 data using a lutetium resolution model as kind of a bad projector, and then as what we call a good projector using this same lutetium resolution model, but adding a Gaussian blurring, which was based on Gaussians that were fitted to Bremsstrahlung range data from GATE. So yttrium-90, you can image it with Spect imaging by using the Bremsstrahlung X-rays created from the electrons that are emitted by yttrium-90 interacting with charged particles in the body. And so we had 12 subsets, 15 epochs, and updated the correction every 5 epochs. On the left here, you can see the results with a bad projector, in the middle with residual correction, and on the right with the good projector. And down in the middle there's a plot of profile through the large sphere. And you can see that the residual correction, even with only, so this is 2 Monte Carlo forward projections, is quite similar to the good projector. And so we thought this was good and went on to apply this to some real data. So firstly, lutetium-177, this time with 16 subsets, updating the correction every 5 epochs in the same way. And shown here is the residual correction for the final Monte Carlo simulation, but a projection and a sinogram, so you can kind of see what the residual correction looks like to that additive estimate. And then on the left of these images, we've got the OSCM image without any residual correction, and on the right, the OSCM image with residual correction. I don't know how easy it is to see there, but the edges visually look sharper. And if we look at these profile plots, we can see that there's been an increase in the value of voxels inside the sphere without any increase in the noise on the outside. And we see something similar with Yttrium 90. So this is 12 subsets with 15 epochs, and we update the correction every 5 epochs. And again, there's the difference images for the residual correction, for the projection and sinogram. And again, we can see that there's a marked increase in the voxel values in the spheres with very little and even less noise outside of the spheres. So this is all really preliminary stuff. So this doesn't necessarily mean that the reconstruction is better. So what we need to do later is run the same stuff with some simulated data where we know the ground truth. So in summary, we've improved the SIRF SIMIND connection that was presented at last STIR user group in Vancouver with a fully Python API. And hopefully very simple and easy input and output SIRF data objects, and demonstrated that this can be used for some reconstructions in SIRF with the residual correction method. Thanks for listening. So I'd like to ask a few questions, whether this is actually useful to anyone. You don't have to say it now, but you can email me at that email address at the bottom. And if anyone would like to see anything slightly different with this method. So thank you.
Any question?
Okay.
Yeah, I'm looking online, but I don't see.
How do we say online?
Just close your slides.
Is it Zoom?
Yes, Matthew, yeah, you can go on.
Oh, I was just applauding.
Oh, thank you.
Okay. Okay, then.
That was a very good talk, though. Yeah. What are your plans with this? What kind of things do you think it could improve in the clinic or in other realms of nuclear medicine?
So the reason I first kind of got interested in this is that I'm doing synergistic reconstruction with Yttrium 90, and using priors that rely on edges, and without kind of proper resolution modeling, these priors don't really make any sense, and it's very difficult to get good resolution modeling in Yttrium 90 Spect. So hopefully this will improve the resolution modeling using this residual correction so that these priors are more effective.
Okay, cool. Well, best of luck with it.
Cheers.
I have a question which is a bit weird because of my co-author, but anyway, Sam is doing everything. You mentioned subsets, so can you say in your SIMIND interface which views you want to have, such that you only do those for a certain subset, or how would you handle that?
Yeah, so at the moment you can't yet tell. So there is a different projector class that I've implemented for this residual correction stuff, and for most of the time that acts like a SIRF forward projector, so you can tell it which subsets to use. But if you want to use this residual correction, then it's a separate method. So at the moment I'm having to create a function, do a certain number of epochs of OSEM, and then run this method to do the forward projection. Does that make sense?
Yeah, I mean, I sort of think it becomes very difficult to see how you would extend this algorithm to subsets anyway, probably.
Yeah, it's something that I haven't think
maybe
about.
combining it with something like SVRG or so might be the thing to do, because then you need to have a full forward projection anyway, and at that point to do Monte Carlo something.
Yeah.
All right, great. Thanks, Sam.
Cool. Cheers.
Good results in the end.
Yeah, finally.
All right. Thank you, Sam. So the next one is Nicole Juriew. Sorry for the pronunciation. On GPU accelerated time of flight path reconstruction via still integration of Parallelproj. Sorry.
Hello, everyone. Sorry. My name is Nicole. I'm also Chris's PhD student, and I did a bit of work on GPU accelerated time of flight PET reconstructions via the STIR integration of Parallelproj. So the time of flight functionalities have been integrated into STIR master since version 6.0. But the traditional STIR ray tracing projector does not support GPU utilization. Parallelproj, on the other hand, is an independent CUDA and C and Python library, which allows the use of CUDA GPUs for fast tomographic projections. And since STIR version 5, we have had a wrapper of Parallelproj for non-time-of-flight reconstructions or projections. And what I did earlier on is that I extended the wrapper's functionality to support time-of-flight data processing. So I'm going to show you some results, more or less, on PET phantom scans of the Siemens Biograph Vision. And we scanned a NEMA IEC body phantom. For the data generation, we still rely on the Siemens research software E7 tools that unlists our list mode data into sinograms and estimates the time of flight scatter and randoms. Sorry. We then have a script that can transform these Siemens-generated files into STIR-readable files. That means, for instance, the time of flight bin order is different in the Siemens data as it is in STIR data. It also means that Siemens only outputs 2D scatter. We upsample it to 3D scatter, and so on and so forth. This conversion script to process the 7 tools output will be made available. We have only just gotten the go-ahead from Siemens to publish, well, to make it publicly available. Sorry. Okay, so for the reconstructions, I was using STIR via SIRF, and I used MLAM reconstructions using 10 iterations. So this is important to mention. So for the STIR ray tracing projector, we had to set the number, we set the number of lines of response per sinogram bin to 5. When you set it to a lower value, it can produce artifacts. For the timing tools, what we did is for the individual steps, so for the forward projections and back projections, we used the STIR integrated timing utility. And for the full reconstructions, we used a Python module line profiler. Sorry. And then it's important to note the file sizes as well. So the prompt sinograms that we get from Siemens are 1.4 gigabyte big. They're signed integers. But overall, once you read them in, randoms and scatters are 2.8 gigabyte large. Because they're saved as single floats. And that's necessary to mention because due to these large file sizes, we had to switch caching off in the ray tracing projector, because otherwise we would have just run out of memory. A little bit on system specifications, kind of boring, but still important to mention. We used, or my system has an Intel Xeon processor, which can use up to 36 threads. My RAM is 64 gigabyte large. My GPU is an NVIDIA RTX with a VRAM of 16 gigabyte. And yeah, I also noted the software version. So STIR was 6.3 and Parallelproj was 1.9, which I think, yeah, and CUDA is 12.1, which is probably the most important versions here. So there's a note on overhead that I give you before I present the timing results to you. And that's because, there's an overhead when we project the data. And especially because we're copying data from the CPU to the GPU, and not just once, but multiple times. So the procedure is, if the image is stored non-contiguously in memory, we copy it to a contiguous memory block, but that rarely ever occurs. So that's grayed out, basically. We then copy the image from the host to the device, to the GPU, where we then call Parallelproj for all data. Currently, Parallelproj is implemented into STIR such that it's not called subset-wise, but always for all data. The projection data is then copied from the device to the host. And then Parallelproj and STIR projection data, again, use a different data order. So STIR groups by time of flight bin first, and Parallelproj groups by time of flight bin second. So there's a transpose function there's a function that transposes from the Parallelproj order into the STIR order then. And that happens on the CPU to an internal proj data in memory object. STIR is set up to forward project directly to a file. And when the data is then accessed, it's copied from the file into memory again. So the consequences of all of this basically is that we need double the memory because forward project uses an internal buffer, but the transpose function uses its own buffer again. And then there's also an overhead in memory copies because all these steps up here are not just done once per reconstruction, they're done once per iteration. And also when you only want to, or only need this for a subset of the data, there's also some overhead because you always do the full forward and backward projection and then just access a subset of the data. So this is just to explain to you why on the next slide, some numbers are, well, don't go linearly maybe. But even though we have all these, this overhead, there's a very large timing improvement when we use Parallelproj versus the ray tracing projector. So a simple forward projection of all the vision data that I just showed you takes 5 minutes for the ray tracing projector and 0.5 minutes with Parallelproj. And you can see on this table that, well, without any question, there's a massive time improvement. What we then also did is that I thought it would be good to show you reconstructed images as well. Looks like it works. They are artifact-free. What we had a closer look at were also, so we compared the forward projections of ray tracer versus Parallelproj, but we had a look at simulated line sources because it's just easier and it catches the eye. Yeah, there's a clear, you can expect to find a clear difference when you forward project the line sources versus some real data. So this is just to explain the following plot to you. So we created forward projections of these line sources, and we then plotted the TOF bin over transaxial distance so this is specifically for view 0, and I'm always showing the central direct slice. And I plotted all of these for all views and stacked them together. And this is what you see here. I hope this was sort of clear. I see now that despite my efforts, you cannot see anything here. But I will show you the difference of those projections on the next slide, which are hopefully a bit better, can hopefully be seen a bit better. So these are the differences with respect to the maximum in the ray tracing projections, and we look at differences of plus minus 1%. Of course, that was just for the central TOF bin. This is a bit odd, sorry for that. And I now stack together, I plot view over transaxial distance and stack these together per time of flight bin. And also here, we can see that the differences are quite within some acceptable limits. Okay, that was it from my side. What I do want to do in the end, of course, is to thank our collaborators. So special thanks go to Georg Schramm, who helped me a lot with this work. And then we would also like to thank Judd Jones, Paul Schleier, and Mohammad Reza Temurizi-Charni for their support. And then, of course, also it's great that they do allow us to make this script publicly available. Thank you very much.
Thank you. Do you have any questions? Oh, all right. I will bring you the microphone.
Thank you. Is the calculation done in 32-bit or 64-bit for both cases?
Sorry, I didn't quite.
So calculation is 32-bit of float type or double precision type?
So the sinograms that we get from, okay, so the list mode files from the vision are in 64-bit, but we cannot, with STIR, we cannot read the list mode files at the moment. There has been done some work, and I'm not sure how ready that is. So we can't read that. So we need to use the sinogram output from the 7 tools. And their prompts are output as an integer. I don't know if signed or not, but I think it's just a normal integer. No, unsigned, because they're prompts. They're all positive. And then we have scatter and randoms, which are then in a single position.
Single, okay, thank you.
Thank you. Hi, Nico. Sorry. Just a quick question about the timings, which I was quite surprised. So that was what I expected, that back projection would be taking longer for the is it the standard RT? I don't know what does RT stands for.
Oh, sorry, that's the ray tracer.
Oh, but
That's the
within
stir rate
they are
tracker.
the standard one. Okay, so that's what I roughly anticipate. But now, when you go to the GPU version, actually back projection is faster, which is odd from my perspective. Can you comment on this? Why that could be happening?
So I briefly talked to Georg yesterday. He's here at
Yeah.
the conference, and I asked him if maybe what is happening is that when there are bins with zeros, maybe he ignores them. He doesn't back project, or he ignores bins with zeros.
Right.
And he said, yeah, that's what's happening. But then he checked his code and said, no, actually, that's happening for non-time of flight. But for time of flight, he still needs to implement that, because you can't just look at the sinogram bins. You need to sum up the counts along the entire line of response to then ignore it.
But if you, I would still agree. I mean, I don't agree, but I agree with your first version that you know, when you have a time of flight, it's still a separate sinogram, which is zero. You don't back project it. Simple, no? It's by default it's zero, right? So if you add, then it's in another. You put another time of flight sinogram. Then you, if it's non-zero, then put it back into the image. Am I wrong?
Yeah, Pavel, I think I'm not sure, but I think Georg is doing all the time of flight bins together in some sense. So they would need to be all zero before he can skip a whole LOR.
That's what he said.
So that's implemented. So so that's how it's implemented.
Right.
But he doesn't perform this check. So I thought that that's why the back projector is so amazingly fast.
But if it's still all of them have to be zero to ignore it, still you will have some sinogram bins which are zero when you don't project anything. I mean, yeah, even when it's mashed to, I mean, when you ignore time of flight. So maybe it's still kind of true, because it's, I mean, it is possible. I mean, from my perspective, it is possible to make back projection faster, but it will be implemented differently. When you implement it differently, then you have a mismatch between forward projector and back projector, and that's a lot of mess. So I would imagine that he uses consistent forward and back projector, and if that's happening, back projection is always taking more time, so which shows in the first column, you know, in the standard one. So that's why I was kind of surprised. It's a tiny little thing. I mean, enjoy the live when it's so beautiful, but
no, you have
it's
it.
still,
It's a good point. It's
yeah.
quite surprising. Yeah.
All right, more questions?
Very nice work. I think, in my opinion, it's because the sinogram bin and is quite sparse, and when you back project in the GPU and your denominator is zero, and you don't project anything, that saves a lot of time. Maybe you could check if you have more statistics. I think the back projection time should possibly improve that. My point is that it seems that there's missing parameters here, which I don't know what's the iteration, how many iterations you done, what's the subsets, and how many minutes is the data.
Yes, so I should have put that on the same slide, you're right. So the reconstructions were not divided, so the data was not divided into subsets. I used MLEM, and I used 10 iterations, which is debatable, but the point was just to compare the timings with each other. So, yeah.
Yeah, got it. I think in other slides you have an IQ image quality 0.1, and the sphere is off center. Is experiment dedicated in that way, or is abnormal? I mean, the sphere is quite near the edge of the scanner.
Yes, it is. Yes, that's yes, that's
how the experiment has been done.
That's how it has been done. It's an Earl thing. So in our clinic, they do some Earl scans, and for those Earl scans, they need 2 bed positions for some reason, and that's why.
Okay.
This looks like
one
that.
last question that you mentioned the number of errors that has been set to 5. And below that, you're probably going to encounter some artifacts. Why? Is that any comments on that?
I'm afraid I don't know that. That would be a good question for Chris or for people who've worked with STIR more than me. I don't know.
Sorry, can you repeat the question?
So, sorry, why are there artifacts when you set the number of line of response per bin to 1?
Oh, all right. So it's so the default projector implements ray tracing, and ray tracing doesn't take voxel sizes into account in some sense. It just has one LOR. It also doesn't take detector size into account. So that means you are going to have discretization artifacts. So if you use multiple rays, then these discretization artifacts get averaged out a little bit. So exactly how many you need depends on your voxel sizes and the ratio between the voxel size and the bin size and things like that. But so we use something like 5 or 10 or something like that, tends to give much better results. It also implies you have some resolution modeling as part of the ray tracing projector if you use multiple lines. Now the Parallelproj implements a different projector. It's a Joseph's projector, which essentially works by interpolation. So you interpolate where the voxel center goes into the Silingram bin in some way, and it's therefore a bit well, it's less sensitive to discretization artifacts. So to do this comparison, we thought it was somewhat fair to run both in a way that you wouldn't have too many discretization artifacts. At the initial iterations, you don't really see any of this, but if you keep on iterating, then you will start to see a difference.
Have more questions?
Hi. Firstly, thank you for your work. I think that's really important for STIR. When I try to use time of flight in STIR, I think that I found that this is only implemented so far for the cylindrical geometry and not yet blocks on cylindrical and generic. Is this correct, or did I not get deep enough into the topic?
I would say that that's correct.
Yeah, that is correct. Unfortunately, there are a few people who have asked about this recently, so I guess we'll need to raise it on our priority list, and help will be appreciated as always. The reason is more or less only history. The blocks on cylindrical and the generic excuse me, scanner configurations were contributed by Parisa Kateri from Zurich, and she did that work during her PhD, independent of the rest of the STIR development, while all the time of flight stuff was going on. So when she started this, we made the decision that she would develop in a way a parallel hierarchy for the projection data. And the way that hierarchy works is a little, at the moment, when we merged it's a little bit reversed in a sense. So some of the basic functionality is not shared between the blocks on cylindrical and the cylindrical hierarchy. And that functionality is where some of the time of flight information sits. So we essentially need to flip the order in the hierarchy, and then this will work. But it's it does need some understanding of C++ and of the underlying concepts, and then it will need some good validation, obviously. So help would be very welcome.
Okay, cool. Thank you. Another question just came into my mind relating to the last question. For the sampling, when you take multiple lines of response, I do understand that you get artifacts when you don't do that, but couldn't you, instead of projecting multiple lines of response, which is sampled from the crystals, use something like tubes of response? Does that make sense? Is this computationally efficient? Could you actually do that instead of sampling?
Yeah, there are papers on using tubes of response in 2D. This is fairly easy, and in that case, it's called strip integrals, and I believe Jeff Hessler's original image reconstruction toolkit uses strip integrals essentially to avoid those discretization artifacts. In 3D, it's just a little bit harder because in 2D, the intersection of a strip with a square, okay, we can all compute it. In 3D, now you have an intersection of a tube with a voxel. It just becomes complicated. But some people have done it. We just don't have an implementation of it in STIR, unfortunately.
Okay.
There is I think it sits in the experimental code in STIR. We did make ages ago with Matthew Jacobson. We made an approximation of that strategy and actually incorporated solid angle effects in there, which more or less said that at some level you can do this calculation without thinking about the rotation of the voxel with respect to the tube too much, and then you at least get closer. But that hasn't been tested or validated in ages. So if you'd be interested in that, that would be major work, I think.
Thanks.
I have one question. Can you go to the slide with the scanner? You have like
Yes.
right. So I understand that this is Vision 600.
Yes.
And there is a body coil there, isn't well?
Yes. Thank you for that question. No, so I'm performing work on MR hardware attenuation correction, and we're comparing the results for non-time of flight and time of flight data. And I realized that when I did the experiments, of course, I did a ground truth PET scan, but I didn't take a ground truth photo for some reason. So I decided I'd leave it on here. It would still look funnier than without. So yeah.
All right, let's thank Nicole once more.
Thank you.
Is Tommaso Ferri on 3D spec modeling integration for channel edge pinhole collimators into the open source STIR framework.
Okay, so good morning, everyone. My name is Tommaso Ferri, and I'm a PhD student from Politecnico di Milano who did an exchange program to UCL for 6 months. And I'm going to show you today my tiny contribution to the software, so by adding the channel edge pinhole geometry to the STIR code. So for this work in particular, we focused on the pinhole Spect software framework, and which is responsible for the evaluation of the pinhole system weight metrics for pinhole spec systems by taking information about projections, detector file, and collimator file, like the geometry of the collimator and the type of the collimator, but till now only knife-edge collimators were supported. These information are then used by the projector called the Projmetrics by beam pinhole Spect hub, which determine the system weight metrics by evaluating the contribution that each image voxel of each image voxel along the line of response to each detector element. And my contribution was in this work was to adding to the code the analytical determination of the channel edge geometry implementation, so modifying the code in the projector and the collimator file by adding all the missing parameters, like the possibility to choose between the two type of collimators, and like adding parameters like the depth of the channel. So how this projector works, the projector is, sorry, I wanted to, okay, there's no, okay. The projector is evaluating the area that each image voxel is projecting through the pinhole hole to the detection plane. Here you can see an approximation on the case where only the voxel is moving only in the x coordinate, so the y coordinate is set to 0 for simplicity. And we see that the contribution of the x-axis is actually proportional to the channel size and that ratio, which is where VD is the distance between the voxel and the detection plane passing through the whole channel, so the actual line of response, over VH, which is the distance from between the voxel and the hole. This geometric contribution of the point spread function is then shaped according to this, the size of the hole, which can be round or squared. And when applying PSF correction, this PSF is then convoluted with the intrinsic point spread function of the detector. So when performing the channel edge implementation, the first difference that we encounter is that the effective size of the hole that is projected onto the detection plane changes according to the voxel position, and we can now divide the problem in 3 main cases. And also in this case, for simplicity, we consider a straightforward case when a point is moving slowly in the x direction, so the y direction is set to 0. And we can see here that the main difference is given by the fact that the area which is projected is the one at the bottom of the channel, so the side towards the detection plane. And so the line of response is not now passing through that point H in the middle, but on the point capital H. So even though the formula is for the quantity GHDX is the same, the actual distances VD and VH are different. For the second and the third case are specular to one another, and here we can see the difference is mainly highlighted because while the voxel is moving towards the minimum or the maximum acceptance angle, the area which is projected is actually shrinking. So here you can see to the formula that the area of the hole which is projected is not now coincident to the whole channel of the hole, but it's the total size minus a quantity dx, which is dependent on the x coordinate of the voxel. And it starts from 0, reaching the value of gx while approaching the maximum of the minimum acceptance angle. So also at the same time, the distance VD and VH are changing as well, because the capital H point is remaining while V is moving the center of the area projected. So it's changing as well as concording to the X coordinate. So these changes were made to the STIR software, and of course, they were extended by considering all the variations also in the other directions. And to validate this software, we actually did some testing on and validations on a channel edge collimator used for design for boron neutron capture therapy. That's actually my what my PhD is about. And I'm going to introduce you briefly to the therapy, and I'm going to show you the simulations and the measurements that we did in a real facility of neutrons, and the reconstructions that we obtained with the STIR, with the new implementation. So BNCT, or boron neutron capture therapy, is a radiotherapy treatment which exploits the high cross-section of interaction of a non-radioactive isotope of boron, the boron-10, with thermal neutrons. So in this therapy, boron compounds are injected to the patient. They are selectively absorbed by cancer cells, and then the patient is irradiated by a flux of epithermal neutrons. The reaction with the boron and these neutrons leads to the emission of high LET particles, alpha and lithium, which destroy the cancer cells. So But in 94% of cases, the lithium is released in unstable way, so it emits gamma at 478 kV, which can be detected for dose monitoring and localization. So the Spect system that we are proposing is based, as I told before, on a channel edge collimator with a 5 millimeter diameter channel and a 4.8 centimeter depth. When a gamma is passing through the collimator, is detected by a gamma module that we made in our lab based on lanthanum bromide scintillator crystal, and the light emitted by the impinging of a gamma ray is detected by a metric of silicon photomultipliers that are fed to a neural network for detector image reconstruction. So that's how we acquired the projections. So now that we have all the instruments to perform thermographic images, we designed a setup for measurements at the Trigamark reactor, a nuclear reactor situated in Pavia. Here you can see the, sorry, yeah, do we have the, no. Okay, sorry. Okay. Here we can see a fixed support in which we place 2 vials containing 700 ppm of boron 10 in solution with boric acid and water. And those 2 vials are placed at the corner of a 1 centimeter size square and aligned to the neutron flux. Then we apply some lead shielding to lower the background radiation coming from the BSA of the facility. We have a moving support in which that keeps aligned the detector and the collimator at a distance of 15 centimeter, leading to a total field of view at the vials of 2.5 centimeters. Then the detector was wrapped in cadmium foils to avoiding residual thermal neutrons in the radiation room to interact with the boron, which is present inside our electronics, so not leading to an unwanted emission of gamma at the same energy that we want to detect. So as you can see, the space inside the room is really small, so we had to perform only partial rotation, and we choose only 4 angles, 0, 60, 120, 180. And for each position, we acquired 2 measurements at 70 kilowatt of reactor power, one with the 2 vials filled with boron, and 1 background measurement by replacing the 2 vials with other 2 filled with only distilled water. And at the same time, in parallel to this, to validate the measurements, we ran some FLUCA simulations, which is a Monte Carlo code to simulate the particle interaction with matter. And this software allowed us to replicate the planimetry of the reactor and our system. And the neutron flux that was simulated was actually measured experimentally in the same facility at 10 kilowatt reactor power, and then rescaled to the actual power of the measurements. With this information, we actually extract information about spectroscopy performances of our system and expected reconstructed images to compare with our experimental measurements. Here you can see the main difference. Here we have the images obtained with the FLUCA simulations that were obtained by taking for each gamma that from simulation is interacting with the crystal, the centroid of all the Compton events. And so not only taking the first photoelectric one. And here you can see the projection that we acquire with our system, and so the detector, the collimator, and the neural network. And you can see that the projection actually match. So we decided to perform the reconstruction with the new code using MLEM. Sorry, I write it wrong. I said OCM, but I'm actually using MLEM. With 10 iteration, you can see that we can reconstruct successfully the profile of the 2 vials with only 10 iterations at the distance that at 1 centimeter distance. So we can conclude saying that the channel edge geometry was successfully integrated, leaving invariant all the previous functionality that the code already had, so nothing changed. And regarding these BNCT results, this software allowed us to finally reach the first tomographic reconstruction of boron samples in the field of BNCT, which is a very exciting result. This represents a very first step towards the building of a full system for the monitoring of this therapy. I'm actually giving a talk about this and details of all the electronics, the systems, and more detail of the measurements on Saturday, 2nd October at 10:20 a.m. if you're interested. So thank you for your attention.
Thank you. Are there any questions?
Yes. For the modeling of the pinhole, it looks like it was just a geometric model.
Yes.
It didn't include septal penetration.
No. No. My contribution was only to replicate the geometry by calculating the geometric value of the PSF. So I'm not applying any septal correction.
Yeah, but the whole point of using the channel instead of a knife edge pinhole is to reduce the septal penetration. So it seems to be an important factor.
Well, yes. I mean, the steer code is evaluating all these areas, so evaluating all this the contribution of each voxels, and then from this voxel is going to evaluate the weights, taking into account also the sorry. No, I didn't think about that. I don't know if Chris can say.
I think Shell is correct that the way that originally the modeling was done by Carles Falcon of the knife edge, it doesn't do collimator penetration. However, I sort of think that's less important for the channel edge because you will have less collimator penetration for the channel edge than for the knife edge. So for Tomas's work, I think he's in luck.
Okay.
So I think that the modeling that is purely geometric will be okay for a channel edge one, as long as it's thick enough, obviously. Might be wrong.
All right, I have a question. Is this code already available in the STIR framework, or you haven't merged it yet?
I don't know. I don't think we made the pull request yet. No.
Not yet.
The next update.
All right. Chris, would you like to add something?
Yeah, I think this is probably more an oversight than anything else. No, we haven't done that pull request yet, but it's all available, obviously. So I guess Tomas and I need to sit together.
All right, brilliant. Let's thank the author once again.
Okay.
Hi, everyone. My name is Spencer Manwell. I'm an imaging.
Sorry, the next speaker actually couldn't make it today, so he recorded a video, and we're going to play that. So yes, so the next one is Spencer Manwell from Convergent Imaging, a company, and he's going to talk about evaluation of STIR for commercial purposes.
Physicist and software developer with Convergent Imaging Solutions. We're a company based out of Ottawa, Canada. And I was invited to give this presentation to describe some of the work that we've been doing with STIR recently to try and implement a commercial Spect reconstruction application. So this work has actually been fairly collaborative with Daniel Dita from the National Physical Laboratory. And he was also the one to invite me to give the presentation. So thanks, Daniel, very much. So the talk is called Out of the Lab and Into the Market, Preliminary Evaluation of STIR for Commercial Spect Reconstruction Software. So just to give you a bit of background about who Convergent is and things that we do, we're a software as a medical device manufacturer. The company's been operating since about 2007. Our primary product is called Unison Molecular Imaging, which is really just a workstation software platform for radiology and nuclear medicine professionals to analyze and process and read diagnostic images. Our company has partnerships with several PACS vendors and other software vendors, some of whose logos I've included on this slide. Time ago, we were approached by some of our customers who were interested in Spect reconstruction software as a product to include it at their clinics, and so we started thinking about including such a feature in our software package for the first time, which is why we started looking at STIR to try and address this need. So some of our customers represent clinics with older scanners whose vendors are no longer providing software updates or upgrades for those systems. Others might be clinics with multiple scanners from different vendors, and they're looking for a harmonized solution for Spect reconstruction across the different models of scanners that they have access to. We're a relatively small team at Convergent, and we don't really have the in-house expertise to drive a project like this from scratch. So we started looking at open source solutions to try and address this need for our customers. So there were a few different packages that we looked at, things like Pi tomography, Castor, and STIR. And so I'm just going to spend a moment and discuss some of the thoughts that we had about these different applications and why we chose STIR out of those three. To give a little bit of context, our customers are largely non-academic imaging centers. So these professionals are really focused on kind of bread and butter imaging techniques, reconstruction techniques, and aren't necessarily interested in the most advanced software products that are available. So really, the things that we need to satisfy for these customers are really standard functionality, with a large emphasis on software being very reliable and also high performing. Another requirement that we had to consider is the fact that all of our centers customers really operate with image formats that are in the DICOM standard, and so making sure that support for that file format is present is very important for us. So looking at Pi tomography, Castor, and STIR, they generally have very similar capabilities in terms of Spect reconstruction software. But looking at a bit more closely and comparing these options, Pi tomography and STIR seem to have the most complete solution. And so we kind of honed in our focus on these two a little bit. And so these include things like the different reconstruction algorithms that are available, different data correction options and algorithms, as well as support for the DICOM format, like I was mentioning already. We spent a bit of time on this, and without going into too much detail, we did lean into STIR, and so that is kind of the direction we're going in at the moment. And STIR is the software package that we're spending some time with at the moment. And some of the things that really made a big difference for us were considering things like the code maturity of STIR, some of which has been around, I think, since the mid-late 90s, as well as the fact that it has a very active user group. All of you who participate in meetings like this to share and discuss ideas about the software, what it can do and where it can go. And we feel like those aspects really make us a lot more comfortable in using STIR in a commercial platform. So I'd just like to comment on some of the challenges that we foresee with the use of STIR looking forward. So after installing STIR and getting it up and running and testing it out, we realized pretty quickly that there is fairly limited support for reading in projection data in the DICOM format at present. So this is something that we spent a bit of time on, and we'll discuss a bit more in the coming slides. And additionally, there was really no support for generating output reconstructed images in the DICOM format. So these are things that we'll be spending some time on our side to get this ready for commercial application. Some other things that we haven't really yet had a chance to look at very much, but we think will be pretty important for us, is the ability to generate attenuation correction maps for use in the reconstruction. At present, STIR has fairly strict requirements on matching the extents and spacing of a attenuation map to the reconstructed SPECT image, which is not something that's very convenient in a lot of cases. So this may require a lot of manual registration, resampling to generate the attenuation map to make it available prior to reconstruction. So we feel like we need to streamline that workflow as much as possible, or potentially reduce the restrictions that STIR has on this part of its reconstruction. Another thing that we'll be looking at is the resolution recovery techniques that are available in the SPECT component of STIR. So it currently supports 2D and 3D resolution recovery techniques, which are based off of kind of a Gaussian blurring kernel and working that into the forward and back projectors. So the 2D approach is relatively quick, but also seems to be introducing some kind of local artifacts that because it operates in plane and it doesn't spread across the Z domain of the image. The 3D approach is certainly more accurate and provides better image quality, but can be very slow in operating for some scanners and some collimators where those correction factors become big. And so we see this as being kind of a major consideration of our focus going forward, and we'll talk a bit more about this later on. Some of the work that we've actually had a chance to do since starting with STIR is mainly involving this support for DICOM, like I've been saying over and over again. So we've looked closely at the utility Spect DICOM to interfile that was written by Ben Thomas, Daniel Dita, and Chris Thielemans, and looking at making modifications to it to support SPECT projection data that were acquired on multi-head SPECT cameras. So there are some current issues, 1102, 1184, in the GitHub issue page that are related to this. And these are some of the things that we've been trying to tackle at the outset, and we've had some success with, which is great. So really, the existing code was not designed to handle DICOM inputs where there were multiple heads, and so we needed to extend its capability to look deeper into the DICOM file at the additional detector sequences to extract information that would help us determine things like the number of projections that will actually exist in the data set, the rotation radii of both detectors as they orbit around the patient, and the full extent of rotation. And so really the changes that we've had to make here are, like I was saying, looking into the detector information sequence in those DICOM projection data sets, and going into each item, which corresponds to unique detector heads, and extracting all the information we need so that the interfile object that gets produced for the SPECT projection data encompasses all of that information. One issue that we encountered, which is related to this same utility, was its inability to handle certain type of DICOM files. So we found actually that when a DICOM image is written with a transfer syntax that corresponds to a compression in the data set, that the utility was unable to actually read the projection data buffer from that DICOM file. And this was also logged in the GitHub page as issue number 1474. So really, this was a non-starter in any case where clinical systems are generating DICOM files in this format, and we happened to encounter some early on, which tipped us off to this being a problem. We implemented a change to address this issue, where we would actually attempt to read the DICOM data set. If we failed, we would check the transfer syntax and see if it corresponded to a compressed syntax type, in which case we can use the existing tools included in the ITK library to rewrite that file in a non-compressed transfer syntax and then reread it back into the system. I believe there's another STIR user that's been looking at an issue like this, and I guess the hope is to try and merge these solutions and possibly avoid the need to write a temporary file, which we then have to reread. So this one's still a bit of a work in progress, but the solution that we have now is at least able to tackle this case whenever we encounter it. Once our reconstruction is complete, so we're looking at the other end of the spectrum now, we are implementing a tool to take the interfile object that STIR generates and reformat it and recast it as into the DICOM format. So the utility that we're working on is called the Spect interfile to DICOM. The basic way that it operates is to take information from several different sources, combine it, and to generate this the DICOM image. So from a lot of the DICOM header information we'll retrieve from the original DICOM projection data that we'll retrieve from our users, that they'll effectively pass into the reconstruction. So things like patient information, study information about the radiopharmaceutical, and also details about the detector information sequence that is embedded there. And these are all things that get lost in the conversion of that original DICOM file to the interfile format of the projection data. From the interfile image that STIR generates, obviously we're going to get the reconstructed image, so the buffer, and then details about it, like its extents, the pixel spacing, and things like that will also get incorporated. And lastly, there are additional DICOM fields that correspond to the mechanism for actually generating the image. So we want to extract from the reconstruction parameter file details about the byte encoding, the reconstruction algorithm that was used, potentially any post-reconstruction filtering that the user chose to apply, and also insert that into the DICOM header as well. So using information from these different inputs, we can stitch them together and recast the reconstructed image in the DICOM format. There's still some things that we're working on this front because we don't have access to certain information that would be ideal to include in the DICOM header. So things like the creation time of the reconstructed image is not necessarily logged anywhere in any of the output files, as well as allowing input of a series description or an image ID to help users be able to actually characterize the image and describe it. So these are some of the things that we're looking at now. But we have this utility up and running, at least on our own system, and it seems to be working pretty well so far. Well, as I approach the end of the talk, because I'm running out of things to talk about that we actually were able to work on between now and when we started, I thought I would just present a couple example reconstructed images. So what you're looking at here is a Tech 99M bone scan that was acquired on a Siemens-Symbia Spect CT system. And I have two images side by side, one which used the 2D resolution recovery method and the other that used the 3D version of the resolution recovery. So I'm showing images that are resliced along the coronal plane and the transverse planes in the upper and lower rows to try and emphasize some of the noise characteristics that we're seeing between these two approaches. So if you look at the images for the 2D resolution recovery, for example, you see a bit more noise apparent along the coronal view, but the same noise sector is not really apparent when you look at the transverse. So the noise that you're seeing is really limited to changes in position along the Z domain within the image volume. And so it seems to be an artifact of the limit of the 2D resolution recovery factors, and that noise effectively goes away when you look at when you implement the 3D resolution recovery approach. So once again, you're seeing similar noise characteristics across the two transverse images, but improved noise characteristics in the along changes in the Z position in the images, so that. That's kind of an indication for us that's definitely the approach that needs to be used. But as I mentioned earlier at the outset of the talk, is that the 3D resolution recovery implementation can be quite slow. And so this is something that we're looking at trying to incorporate some acceleration techniques into the computation of the projection matrices when resolution recovery factors are being incorporated to see if we can accelerate that and speed it up so it's not a barrier for use. So with that, that really brings me to the end of my presentation. So just to kind of wrap up, looking ahead, we want to continue and kind of finalize the work that we've been doing related to supporting the DICOM format with STIR. So I apologize to Chris Thielemans. I think I promised some pull requests for these for my changes quite some time ago, and they haven't made them yet. So these are coming. Sorry for the holdup. And some other things that I mentioned that we'll be looking at is streamlining the process of this MuMap creation to make it easier for users and for us to actually implement and offer as a a commercial solution. Investigate these acceleration techniques to speed up the reconstruction whenever a resolution recovery is being used. We'll be building a UI component that will be launched from our existing software that can execute the reconstruction. And once everything is ready, really we'll be focusing a lot of our time and effort on validation of the reconstructed images using data from our users to push that forward. So with that, I'd really just like to say thank you. Thank you to you, the STIR user group, for your attention and for listening. I'd like to say a big thank you to Daniel Dita for all of his help and support, spending time with us to try and get STIR up and running and help us address some of the problems that we've been running into. And I'd also like to give a big thank you to Chris Thielemans for being for providing feedback and guidance and for being so active on the on this in the STIR group and on the GitHub page and providing so much support to not just myself but many users. I'm sure I and many other people appreciate it very much. So thank you all once again. I've got my contact information just below on the slide, so if you have any questions or comments and you'd like to reach out, please feel free to do so. I'd love to hear from you. So thank you all very much. Bye.
Cool. So yes, indeed, contact him if you have any question. I really cannot add anything more than what he said, as yeah, he did all of the work. I just helping navigate through STIR functionality. So yeah, let's go. Oh, there is a question.
Yeah, I think I can probably, although I haven't been working with you guys at all on this, I probably could have made that presentation for PET. I have a couple of comments on it, and I think I found exactly what. Sorry, I forgot the author's name. Sam, I think.
Spencer.
Yeah, I think I've been experiencing the same thing. Is DICOM's really hard. It's hard for PET. It must be brutal for Spect, just because of how the format is set up. It's easier for PET, but there are challenges throughout the whole thing. Different scanners are really difficult to match properly. There's never sort of a tag saying this is what type of scanner it is. You just have to know what scanner it is. Every vendor uses slightly different variations on their DICOM tags and things like that. Do you know how much they've worked with multiple scanners, or have they only looked at one?
So they're using publicly available data. So there are all sorts of scanners that they are looking at. And so they have Siemens, GE. I gave some Mediso data as well.
Yeah. Then the only I will contact the author, him as well, because I think we can share a lot of sort of experience and maybe help each other out a little bit. But my recommendation for this kind of thing is to not use interfile at all, and just to write wrappers around it all and extract the data and go for DICOM, reconstruction, DICOM. The going via interfile is so hard, because you're just adding it. If you're going DICOM, interfile, reconstruction, interfile, DICOM, you can just cut that out by writing wrappers a little bit. That's all I kind of wanted to say.
Thank you, Robbie.
I'm also just kind of wondering, based around what Robbie was saying there, questioning what kind of scanners they're looking at with this. If they're going in the commercial direction, what kind of collimators will be supported? Because so far with the Spect UV projector, only parallel hole, and I think maybe some converging hole has really been inspected. But if you want to look at the whole realm of other collimators available within Spect UV, and then also potentially even with the pinhole code, I wonder what kind of further validation would be required to, make this actually a strong item on the market, if you will.
Yeah, I mean, can't talk on behalf of the company, but I think what I understand from them is that they want to support as much as possible from the spec, from things available in the clinical routine. Oh, battery low. Just a second.
Maybe Chris might be able to comment on this, but how exactly does that work when you have like an open source platform like this under the Apache license and everything going into a commercial product?
Yeah, that is a very interesting topic, and I think this is becoming more and more relevant because there are more and more people who are looking to use STIR in commercial applications. So we intentionally have chosen the Apache 2 license to allow that. So originally, for people with a long memory, STIR was released under LGPL and some bits under GPL and so on. And many people do that as a measure of protection in a way to make sure that people don't run away with their contributions. And then if a commercial company wants to exploit your stuff, then they can come and talk to you, and you negotiate some license and get some money or whatever you want to have. So we don't do that at all. There are many other open source packages that don't that chose open Apache 2, which is a really permissive license. ITK is a big one, but there are many others. And our motivation, aside from just being nice people, I think, is that getting contributions from people is really hard. If you want them to commercialize bits, it becomes a mess, more or less, to maintain. And so at the same time, if you then say, I'm going to commercialize this stuff, but you're not going to get any contributions, well, then nobody is going to contribute. So we felt that keeping it as open as possible was the best way to grow and to have a community, not just of academics, but also of commercial people working on it. And that strategy has worked. Now, obviously, that doesn't mean that we have less money than other people might have. But I do think we have more contributions and a larger community. Now, so Apache 2 is specifically written to allow commercialization, right? So anybody, including Convergent or other companies, can go to GitHub, download it, and do whatever they want with it within certain limitations. But the limitations are really not very big at all. So they can, yeah. Obviously, we hope that they do that and then give us something back. And both Convergent and you'll hear later about Positrico, they are doing that. And Robbie is telling us that he's looking into these kind of things and he's still contributing. So I think it's working okay. There is another question, which is maybe what you wanted to ask. Sorry, this is a long answer. the question is, how do people then validate it as a commercial company? How do they get FDA clearance and things like that with open source software? And that is something that I know very little about, but obviously these commercial people do. And we have asked Marcus Yale from Positrigo to give a presentation on that. In the future, he couldn't make it this meeting because they're too busy releasing scanners now with our software on there. So I'm sort of giving you my next to last slide already. But so probably in January, February, you will get an invite for listening to a seminar on how that stuff can work. So it is possible. And it actually, he says it's not too much work. There is certain procedures that they need to follow and paperwork that and trails that need to be available, but it's entirely doable. It doesn't really matter too much that it's open source or not, apparently. So that's good news for us.
Yeah, that's my understanding with it so far from what a couple of years really is the initial getting FDA approval is brutal. But after that, how the software's updated, as long you really just attach amendments to the software. The FDA doesn't care too much about software compared to hardware. They're much more interested in that.
Yeah.
So I think as long as you do a couple of white papers, and I think as long as no one really objects to what you're doing in terms of software, you generally get it through.
Yeah.
But yeah, I'd like to hear what they say.
Yeah, it will be interesting. Yeah.
Indeed. All right, let's go to the next presentation. Paul Clegg on respiratory motion correction of PET-MR data using SIRF.
Thank you. Yeah, so my name's Paul, and Chris has been looking after me while I've been on sabbatical leave. So this is a use case with PET-MR data. So as you know, if there's motion in the scan, it causes dramatic problems. So the volumes of anatomical regions, their positions, and the quantification, the activities all end up being wrong. So this data of a phantom with a flask inside is available, and so with a relatively simple motion pattern, all hell breaks loose, and you can correct it and tidy everything up. So this motion correction here was done after the fiducial was removed. Otherwise, it's basically trivial. Okay, so I'm not working with phantom data. This is data from cardiovascular patients. So it was taken on the Siemens Biograph MMR, and it's a relatively complex scan sequence. So the tracer is FAPI, and so the patient's having a 50-minute scan, a PET scan, and during that's going on, there's a whole heap of MRI scanning going on. So the bit of the MRI that I have the raw data for is a radial sequence, a radial scanning profile where the patient's free breathing. Okay, and so the team who I got the data from were doing this because they're trying to solve a MuMap problem that they believe they're having. Okay, so I've kind of got the raw PET data, and I've got some raw MRI data, but there's a whole heap of other MRI scans going on during the 50 minutes, which going forwards will end up being useful. Okay, so to do motion correction, then you need to have some idea how the patient's moving. You need a kind of surrogate which is recording. So in this case, respiratory motion. You know how the patient's breathing in and breathing out, and that can be done externally. We've heard a lot about the Neuro Explorer and the camera doing the head motion, right? So that's a surrogate being generated externally. But here, the surrogate information is being taken out of the raw image data. So I'm going to kind of talk about the PET bit first, and then the MRI, and then the consistency between the two. So the way I started out trying to get a surrogate from the PET data is to take the raw data and just take a projection basically straight through front to back of the patient, because if you project through the patient, you can see the diaphragm is quite bright, and so you can see the lungs up here. You can sort of see the armpits and stuff of the patient without any reconstruction or anything going on. And so the diaphragm, which is very bright, is going to be moving, and so we should be able to do PCA on this. And you don't need, so you can kind of crop this right down and just have a small patch. And then, so the first shot at this was then to have half-a-second frames running throughout the 50 minutes, and then use PCA to pull out the breathing motion. That turns out to be way too noisy in practice. So if you kind of look at this bit here, so this is just one end of the breathing cycle, but the data, the loading of the principal component is going up and down by a huge amount, and this turns out to be too noisy to be usable. I'll show the end results of what I've done later on in comparison to MRI, just for consistency, but I'll explain it here, which probably doesn't help. So half a second isn't long enough. It's the time resolution that you want, but it's not enough time to get the statistics. Okay, so what I did instead was break the data up into 1.5 second long frames, and then do that 3 times, offset by half a second from each other. Okay, and then you do your PCA, you create your loadings, but then you can do a weighted sum. Okay, the thinking is the same as for a quadrant photodiode, if anyone's familiar with that technology. But anyway, so you can basically take for every half second point, you take a weighted sum of the 3 contributions, and then you can end up upsampling to a higher temporal resolution. Okay, and as you'll see later on, the noise improves markedly. Okay, so we have kind of a phase space here of the loading versus the gradients of our surrogates, and then this is sort of bin 1, 2, 3, and 4 based on that. And yeah, so I've only drawn bin 1 and bin 3 there, which are at the 2 extremes. And so you can really see the diaphragms moved in those 2 reconstructions. And the scatter and random was got kind of using the list mode to sinogram type utility, and then the scatter to get the randoms, and then the scatter estimation within SIRF. And so I just kind of took the point, sort of extent of the data, which is then the same size as the bin, if that makes any sense, in order to get the proportion of scatters and randoms. Okay, so it's that those aren't estimated for these for the exact data. And yes, so you can then go about motion correction in a variety of ways. So this is then the end. So that's no motion correction. That's with just registering and transforming and adding together. And so you can see it makes quite a lot, where most of the activities around the diaphragm for this case. And that's where you kind of see the big changes from getting rid of the motion. Okay. So MRI, getting a surrogate for the motion is easier. So this scan of the sort of cardiovascular study is done with 18 coils, okay? And so if you look at all the coils and find the one which has the highest variance, it turned out to be coil 3, and then you can basically take the point from the center of K-space and it gives you a nice breathing trace. So this radial scan then is lasts about 4 minutes, and you can kind of see the breathing is quite varied over that, even over that kind of period. So that's what we got. And so you can kind of take the MRI by itself. These bins are inconsistent with the PET ones. They're just something I was doing, but you can kind of see the motion states, and then you can do registration. And work out what displacements you've got. So you're basically seeing the diaphragm moving after registering these to bin 3. So ultimately, I could create the MRI bins to be consistent with the PET bins, and then potentially use the displacement information, because it's much richer, to then transform the PET. Blah, 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 that's kind of correction. So that's also done with registering and transforming and adding. The results when you do motion correction during reconstruction are kind of similar. The kind of heart is noticeably sharper when you do MCIR, but I was getting the kind of streaking noise in the lung was not improving. It was getting slightly worse, so I didn't include that one here. Okay, so just a couple of things on consistency. So it's possible to then put the MRI in the PET space, and that kind of works okay. So there's various cuts through the data here, and it's just marginally odd because the liver dome comes out perfect, the edges of the arms come out perfect, the top surface of the patient comes out perfect, but then the lower surface is off by a bit. So I'm not quite sure what's going on here, but I need to work on that a bit. But I mean, this having this kind of set up then would then allow using going the other way, would allow me to use these displacements to work on the PET, and it also allows makes it possible to do stuff like Daniel's HKEM reconstruction algorithm, which actually works very nicely with this data. Okay, so this is just coming back to my motion surrogates. So the black is the PET and the red is the MRI. And amazingly, there's no need to adjust the timing at all. It comes out absolutely perfect in terms of alignment between the two. So this is just the start of the scan. So the MRI starts after a little bit, and yeah, and then it's all synchronized. And I showed you when I was unhappy with the half-second frames. So this is the same bit in time. So this garbage here is then this bit over here, right? So with my kind of 1.5 second frames and averaging, you get a sensible respiratory motion, which is relatively consistent with the MRI. So going forwards, I mean, what's interesting about this data, or unusual with this data, is you kind of got this epic PET scan during which tons of MRI is going on. So the little bit of MRI I've shown you is from over here, but there's all kinds of breath hold stuff going on, and so the breathing goes crazy because the patient, you know, they're doing all kinds of MRI stuff with the patient in which they're having to hold their breath, and then they start hyperventilating and so on. And so in terms of respiratory motion correction, this is a relatively extreme case, which is something I'm kind of keen to do battle with in the future. So thank you for staying awake, and that was all I had to say.
Yep, any questions?
Nicole is.
Sorry, got distracted.
Thank you. Sorry. This was more something I didn't understand rather than. So this was when you compared the consistency of the PET and the MR data. Thank you. Sorry, is this before or after motion correction, or is this just the PET and MR data that you compare?
Yeah. So then this is. I'm trying to work out, but I'm not sure it matters that much. I mean, this is extremely sharp. So I think this is after motion correction. I couldn't immediately remember, but yeah.
Okay, just so there are two things that come to my mind, and one of them is probably why I had this question is so the. Forget one of them. The other one was, and this is always odd, you always tell people things that happened in your work, and then it's a completely different problem. But what I did is I did phantom scans on the MMR, and I used so there's a Dixon sequence performed on these phantom scans, and we did one thing sort of wrong. Normally you fill the phantom with a saline solution in order to prevent MR artifacts. We didn't do that. We used pure water, and the Dixon sequence was a bit off. And the problem was that part of the patient table was also assigned as patient MUMAP. And I wonder if this is what's happening with your lower boundary. Maybe the MR is a bit further looking into the patient table.
Yeah. Okay. Yeah. No. So I haven't done anything with the to take account of any effects of the table, and yeah, that's possibly worth looking into. Yeah.
Yeah, it might just be that the patient MR AC that's performed just erroneously considers part of the table as part of the patient.
Yeah.
But
okay.
I don't know. That's just something that happened to me.
Yeah. Okay, I will look into that.
Is this the MRAC image?
No.
It,
well, so when I do my PET reconstruction, I use the kind of Dixon MR sequence to generate a MUMAP in a relatively conventional way for PET MR. But the clinicians, so there's collaboration between Edinburgh and New York and Siemens, where they're using this radial scan. So what the cardiologists think is that, well, they can show that the Dixon sequence doesn't get the bronchi right, so it doesn't get the air passages right, and then they think that that problem with the MUMAP is then causing problems resolving the cardiac arteries and other small features. And so they're using this free breathing radial sequence in an attempt to generate a MUMAP which works better.
all right, yeah. Okay, good luck with that, because yeah, we tried that for several months, and it's weird. First of all, you have very clear radials, because from your previous slide, kind of like I presumed that you used GRASP or some version of GRASP around there, and they are much better than the radials that our MMR give.
The kind of the radial scan or the streak.
Yeah, we get all sorts of artifacts.
Okay.
This is not great, but ours are definitely worse. But I see that you have some deformations, and
around all this stuff around the rim. Yeah.
This deformation, right? Usually, depends on why you are using the radial. This should be corrected.
Okay.
Especially if you are talking about attenuation correction, right? Because you see the image there, but it's off. Trust me.
Okay.
Right. Yeah. Great job. And are there any questions? Because I'm not really asking anything right now. Is anybody trying to? All right, so I think it's Chris time. Maybe there is a question. Yes, let's thank the author.
Okay, Chris, I guess you need to share.
All right. Okay, I'm hoping you can see my screen.
Yes, we can.
Excellent, thank you. So, yeah, apologies that I'm not there in person. Would have been great to be there and see you all guys, and then go for a drink afterwards. I'll actually show up in Tampa on Friday late, but so you can still catch me then if you want to and buy me a drink. Yeah, I'll try and give you the usual looking back and forward type of presentation, not keeping you too long because it's late for everybody. Okay, so I'll give an overview of what happened in the previous year, just briefly going through STIR releases, but then also giving you a little bit of information on projects that you might not be so aware of, just to give you some pointers on how that's related to what we're doing with STIR. And then major events that happened in general related to STIR as well. And then some look at the future. So I'm not going to go through these in any detail, but just to give you some information that we had 3 releases of STIR, and then really the version 6 here, which was in February, was a big one, which had the major update to time of flight. So that was a monster pull request that I don't know how long it took us, maybe 8 years or something like that, Nikos, but we did make it. There were many limitations with it, however, you've seen some computation durations from Nicole. The reason that the ray tracing matrix for time of flight is so slow at the moment is that it's not really doing ray tracing in time of flight at all. It is doing ray tracing without time of flight, then taking the matrix and then adding time of flight convolutions in there. So that means it doesn't really depend on ray tracing. STIR, many people don't know, but STIR has a few different types of matrices that you can use. And you can use time of flight with all of those. But it is very slow. So that's a big limitation of that. And Parallelproj was not yet available for time of flight. You've heard about cylindrical scanners already, and the biggie is the time of flight scatter simulation. Was not the only thing in STIR version 6. We made some more progress towards quantitative information by keeping track of radionuclide information and so on. We upgraded our requirements a little bit for both CMake and C++, meaning that we could cut out a lot of old code with workarounds and then finally make impose white space and so on, which is irrelevant for users, but for developers, it's quite important to have this cleaned up because it was getting out of hand. So in May, we had a kind of small update, but a very important one, the Parallelproj for time of flight. Nicole didn't mention Parallelproj can run in CPU, multi-threaded, and GPU. The way STIR does this is to see at compilation time, if it finds CUDA, it will only build the GPU version, and if not, it will only build the CPU. that was just a little bit easier to do. But it means you can use Parallelproj even if you don't have a GPU, and for time of flight, that would be beneficial. For a non-time of flight, it's actually slower than the ray tracing metrics, even if you do multiple rays. Another important thing was the list mode objective functions that were sped up using multi-threading. Before, this was only available if you cache data in a certain way, but this is now available all the time, and that has made a major impact. And there were some bug fixes in relative difference prior and hashing computations. Then in July, we had a version 6.2, which was essentially some improvements in computation time. Maybe too technical to go into, but one thing there, the third bullet, there was a contribution from Imraj, where he put the relative difference prior completely in CUDA as well, because currently our prior calculations are not even multi-threaded. And so he put that in, and that is sort of our first CUDA, straight CUDA implementation in STIR, and can be directly ported to all the other priors and other things as well. So that was a somewhat difficult first step, but will now make things much easier. Yeah, some more big bug fixes, and we now require C++17, which will in the future also allow us to write nicer code. So that's it for the STIR releases that we've had. Onto the other related software. So you've heard from Sam, Nicole, and Paul. They are using STIR mostly via SIRF, not only, but mostly. SIRF is sort of a layer on top of STIR, but also Gadgetron, used by Paul, and Nifty Reg for registration. So it sits in C++ and Python, and you can use it from there. And it's sort of an easier interface to STIR, but it's also less powerful. You can't have everything that you in STIR can do is not necessarily available in SIR. So yeah, just list of releases that happened over there. I'm not going to go into there, but essentially there are many other things happening as well, but gradually STIR gets updated whenever, SIRF gets updated whenever STIR gets updated as well, to make use of its features, obviously. One of the, I think, nice things about the SIRF project is we automatically now build Docker images, and there's a virtual machine with everything on there. So that makes it much easier to deploy it, and STIR is part of that. Okay, so the other project that sits in this space really that we're working with is the Common Imaging Library, or SIL. It is a Python library that the part that we use of it are advanced optimization algorithms, and also penalties or priors, including algorithms suitable for non-differentiable penalties, which we don't have in STIR at all. It was mostly developed for CT, but actually the algorithms can be used, suitable algorithms can be used for PET, MR, and Spect reconstruction as well. And so the SIL at the moment talks to SIRF, and SIRF talks to STIR to do your reconstruction. So actually all our advanced image reconstruction work that we are doing these days is not implemented in STIR directly in the C++ code at all. So the reconstruction capabilities in pure STIR are quite old, and I would say outdated. So we do our development in Python via all of this connection. And in particular, one of the things that got merged into STIL was stochastic optimization, which Robbie worked on in the past. So you have, as opposed to subsets, you can generalize to any sum of objective functions, and then you can try and not just do every subset independently, but keep some history and therefore have better results. So all of that, many different algorithms are available in SIL, and you can do your PET reconstructions like that with much better results than you can get with OCM and so on. So that I'll come back to that in a minute. The other somewhat more tangential project is our emission tomography standardization initiative with the PET raw data. You might have seen my talk about that whenever it was a few days ago. It's a website there. So we've talked about the raw data from Spect scanners being able to reconstruct that with STIR for many different scanners. For PET, at the moment, that is more or less impossible because the manufacturers keep their data, certainly the list node data, mostly confidential, the format. So not the data itself, but the format. Now, in STIR, we've managed to convince manufacturers to release that for some of the versions for some scanners and for some software versions and whatever, but it's very hard, next to impossible, to keep up with that, right? And the ETSI tries to establish a standard for PET list node data so that we don't have to do this thing anymore, which is not just for STIR, obviously, it would be beneficial for everybody. So in particular, the existing formats that STIR already supports, we can then use that to write a converter. So you use STIR as a converter to output PET-cert data. That's something that in previous hackathon, a number of people here in the meeting worked on, and so we'll want to update that. And then the reverse, obviously, we also need to do that. We can read that standardized data into STIR and reconstruct it. That on some level is easy, and on another level is difficult because PET-cert tries to be generic for many different types of scanners, and that would create some challenges to represent that in STIR at the moment. Okay, so we have our second hackathon on Sunday and Monday. If you didn't know about it, it's about 20 people in person and 10 people online that are going to join there to make the next stage. It's going to be mostly, obviously, PET-cert development, but also some STIR for if people are interested in that. And you can still join online, even if the registration page says that you can't, you can. The online experience won't be great for a hackathon. The hybrid hackathons are really hard, but you can at least, follow and see what's going on. And then I think it might be possible to, with a few people who are online and in roughly the same time zone, do some stuff together. So yeah, have a look at that. That's initiative.org. And in any case, if you can't make it this time, you can still do it next time. Last item for the looking backwards is the major event. So we have organized via our Synergy network a rapid image reconstruction challenge for PET data, so PET-RIC. That has now concluded. I did talk about this in the previous STIR users meeting. So for those who don't know, we set up, we wanted to use all our open source efforts to be able to compare different reconstructions algorithms fairly. And it was done on phantom data. And that it was sort of a secondary aim there to sort of make phantom data that people have sitting in their drawer somewhere to make that available. So that was turned out for the organizers anyway, the hardest part of the challenge. But at least there is more data available out there now, which could be useful for anybody who wants to investigate image reconstructions. That needs a little bit more collating, but it is available on the website, and there's a link later. An important outcome, obviously, is that there are now open source software implementations of pretty fast map reconstruction algorithms that are, and it turns out that a lot of them use this stochastic optimization algorithms that I used, not necessarily in the still implementation. Some do, others don't. They made their own. But these are things that are really state of the art and quite promising. Obviously, there's always more stuff coming on. But if you're interested in that, these things are out there for you to just try. And in addition, to make our life possible, we created scripts, and Nicole's is one of those, to be able to handle data that comes in from scanners automatically, as opposed to having to do all these steps manually. And not all of those scripts are available yet. So, for instance, for GE data, we don't have permission yet to share it. But a lot of it, and in addition, there are some scripts to, make some plots and see, is this all right or not? So that I hope that will also be useful for people to use in their own workflow. It was a map with a smooth version of the relative difference prior, and the aim was to get there close. If you're interested, here is the website, and do come to our workshop on Saturday afternoon, where you will hear some more presentations, some more detail on this, but also the 3 winning teams are going to present their algorithms, which will be interesting. Okay, so another major event I think that happens, so the SINRB network has yearly awards for people who contribute to the open source ecosystem that we have. And this year, there are some known faces on there. So congratulations again to Vangelis, Nikos, Nicole, and Nimraj for their contributions. And you will see that a lot of this has been presented at these meetings before. So, that's just a motivation, extra motivation for you guys to contribute and to present at users meeting and, just help everybody out, really. And so congrats to all of these. Then the final event, which I've already sent to the mailing list and alluded to earlier, is that as far as I know, this is the first time that STIR and possibly other open source software will be used in a clinical context. So there are other efforts on this, as you've heard, but I guess Positrigger was there first. So their brain scanner does use more or less vanilla STIR with for the reconstruction. They have stuff around it, for all the DICOM and data transfer and for manipulations and whatever, but so that the actual reconstruction is just implemented in STIR, and it is now FDA cleared and CE marked. And we've had this discussion already. Is this good for us, yes or no? And I believe it is. So thanks for Positrigger to then deciding to contribute actually to STIR and help us all to move forward, not just the company itself. All right, so that's it for the past. I'm taking more time than I thought. Just a little bit on the future then. So, well, the first release is imminent, I think. It's going to be a small one, really, with some minor fixes and improvements that people are contributing. However, we've just yesterday finally found a problem in the tail fitting. Well, not really in the tail fitting. Explains a problem in the tail fitting for the scatter estimation for cylindrical scanners. There will be an issue on it soon, and we have a fix. So that will clear up some problems that we had with unexpected scales and maybe also some problems in the scatter estimate. This was a regression that was, a bug that was introduced 2 years ago, unfortunately. So we'll fix that soon, and therefore the 6.3 release will hopefully not wait for too long. Then there are many other things that have been on the pipeline. Some of them just as long as the time of flight, really. So you've heard about the channel edge already. Another one which it has happened at UCL internally, but we didn't have anybody to actually validate it and so on. GE scanners have, depending on their software version, they store their data in different, slightly different formats. And we support RDF9 at the moment, which is on the Signa PETMR, but also some of the PET-CTs. But actually, at our place, we have an older scanner, and so we will be able to support data from that older scanner as well. Yeah, sorry. The third bullet point here is on multiple energy window support. It's coming more and more. You hear about these things. Budovika did her PhD on this. There is a pull request with all her software on there. It will need major work to merge that with the recent versions of STIR. So this is not going to happen soon, but it is going to happen because we continue this research with new PhD students. There is the motion incorporated image reconstruction. We have, I believe, slightly better but slightly slower implementation of that, which is in experimental at the moment, but I want to make it available to just measure the main STIR capabilities. Something that I find rather painful is that we worked on supporting multiple bed positions and making the coordinate system between scanners, the projection data and images consistent, but it was never finished. So that's already 5 years old as well. We really need to push that. So if you're brave, do give us a hand. And then the last item here, Nicole mentioned briefly, Vietau from Leeds and Groningen has been looking into Siemens vision list mode data, and we more or less have cracked that one. So we're at the moment need to talk to Siemens on how we can make that available to the community as well. So somewhat different from all of that is those are extra capabilities, but we have realized that STIR is still slow, even with the GPU capabilities, and Nicole gave a nice overview of some of the overheads that we have. So we are going to chip away at that, and I'm happy to say that just last week I got a grant of awarded for looking into optimization of STIR to use hybrid computing. So a 2-year grant with some work on that. So hopefully this will therefore happen. And initially we'll sit mostly on the PET side, but obviously everything that we do there will then hopefully be useful for the Spect modeling as well. All right, there are many other things that we want to do. This list is too large. The community is large, but in some sense not large enough. And people, you know, everybody in the audience there, you have your own wish list, and maybe if you're still up for it, we can discuss some of these things later. Things happen depending on priorities from people. If somebody needs it and they're willing to chip in, then it happens, and we do our best to support everybody to understand what is necessary to make the changes. But yeah, there's just too many things to do. All of these are progressing, but all of these are also progressing too slow. So, you know, help welcome. The last bullet point there is sort of very different from all the software stuff. We do, I noticed that our wiki is down actually because of changes in SourceForge, and our website management is from, you know, also 10 years ago. So we need to get away from that. So anybody who has some experience with that would be very welcome to help as well. So time to wrap up. So STIR has been around for a long time, and if you go on our page with histories, you find that actually next year we will celebrate our 25th birthday of open source software for PET image reconstruction, and later on Spect. So we will need to think about some special activities and celebrations and a new paper and things like that. So keep tuned to hear some more on that. So I mentioned contributing already too many times. So how can you contribute? Well, there are all these things, and some of them are really small. Obviously, the longer, the more down we are on the list, the more effort it is. But anything you can do is usually appreciated and makes STIR and all the other associated software what they are. Why would you want to do that? Well, because we're all friends, and we also want to do our bit for science. That makes us feel good about ourselves. But you can actually put it on your CV and not necessarily say, I've worked on STIR, but you can say, I've worked in open source, I've done some C++, Python, whatever. I know about deployment, whatever that you do. It's great stuff that you can show that you have done. There are the opportunities for travel and exchanges and awards. So that's it really. Please, if you use STIR, cite our 2 old papers, so therefore please cite the new papers with the features that you have that you are using. And we have a version-specific DOI as well, although I noticed that there's something wrong with the upload there, so I will need to fix that one. But ideally, you cite that, because then the relevant authors will actually be credited appropriately. And with the acknowledgements side, well, there's a lot of contributors over the 25 years that we need to thank. Also to thank GE and Siemens for allowing us to make some of these file formats public, and Synergy for sponsoring the food that I hope was nice, and giving opportunities for networking, travel, and awards and things like that. All right, thanks a lot. I suggest that we have some a short period of questions if you're still up for it, and then that we try and make a group picture, both from the people locally and online, and maybe even for the speakers as well. But I'll let Daniel and Nikos sort that one out. Happy to take any questions.
All right. So
Matthew, question there.
sorry.
Hi, Chris. Thanks for the update. It's always impressive to see everything that's going on with STIR, and I think the list gets longer every year of the new stuff going on and what's expected to come. So all the best to everybody involved in that. I have a bit of a loaded question. I'm hoping maybe you could give me a little crash course on what STIR has implemented for performing list mode reconstruction, because it seems like there's a lot of different ways that's being used. I'm also curious about the multi-layer detector implementation stuff going on, and how might that be extendable to something like a Compton camera, and if anybody has used STIR for doing any kind of Compton camera image reconstruction.
Right, okay. So the list mode reconstruction is actually is major work from mostly from Nikos, but in the end it is straightforward to use, I think. The only thing you need to do is replace, in the parameter file, there is the whatever it's called, Poisson log likelihood, linear mean, and proj data, whatever it is, with blah 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 and list mode and some specific name, and then obviously give the name of the list mode file. But that's it. That all the rest remains the same. The reason for that is that we have the objective function implementation is sort of in a hierarchy, and as long if you have a Poisson log likelihood function, then any OSEM algorithm or SPS or gradient-based algorithm, whatever, can use that. It doesn't really need to know if it's list mode or if it's sonograms or whatever. So yeah, that is just working fairly transparently, I think. Obviously, one of the things that's quite different potentially in list mode reconstruction versus sinogram is how you decide on subsets. And the way that Nikos implemented this at the moment is to make sure that your subsets between the sinogram and the list mode reconstruction are the same. I think that was a great decision, because that means we can compare the images, and they should, aside from numerical rounding error, and if you didn't use any compression and all of that stuff, they should be identical, and they are, and there are tests on that. However, in the end, that's a suboptimal choice for using subsets in list mode reconstruction. You really want to use you don't want to use geometric separation. You want to use time separation in list mode reconstruction, because then your subsets are much more balanced, and all of these algorithms will work much better. And there are papers on this, and Robbie has done some work on that to say that for some of the algorithms you can use 1,000 subsets without really any penalty, and therefore speeding up things a lot. We don't have that implemented right now. It's a tiny little bit tricky to do when you have radioactive decay and stuff like that, and that's the reason why it isn't in there yet. But otherwise, it's fine. The multi-layer stuff, I think I don't think it would be a major thing, because the generic implementation is sort of set up to be able to do that. However, there are in a few places some wrong design choices made us to assume that the representation of the scanner is a 2D representation. So you go along one direction and along another direction. And if you have multi-layer, that obviously you need the third direction. So those things will need to be changed. So I don't think it's one of these things that will take time, and somebody will need to dive into it to get it sorted. Now, multiple people are interested in it, so I do think it's going to happen, but it does need work, sadly. Compton, I'm not aware of anybody using STIR for Compton cameras. There are components in STIR that would help with that. Obviously, the Klein machine stuff and so on is all in there. Good luck. Yeah, happy to discuss, obviously. Yeah.
Okay, thanks for sharing.
Robbie.
Yep.
I just want to sort of first of all say thank you, Chris, to kind of keeping this whole thing running and being the voice of reason and keeping the project in the right direction. I want to just quickly touch upon kind of an experience of the list mode because it was brought up. One thing I found developing in the list mode is the C++ is painfully complicated, and trying to develop a new C++, a new list mode reader is really difficult. Just because I think the polymorphism and maybe some of the naming conventions are confusing to me. I think it's got real potential, especially if we can get into Parallelproj. I think that Parallelproj is the biggest. I think that's why there's a lot more commercial interest in STIR now, because the speed is now feasible. That's why companies that I'm working for want it. So list mode, I do think there's potential in it in the data, but most people I'm talking to are always interested in just doing sinogram reconstruction as well. That's way more conventional. It's the typical. We always have the conversation that there are still people doing photo-back projection in PET image reconstruction, and everyone's interested in OSCM still. So I'd be interested. I don't know if I'll be able to attend the RIC, but I'd be interested in the results. I think the biggest focus, well, for me, and I found this, I think, during my PhD as well when I was there, is quantitative is kind of key. And I'm hoping I might be able to make some contributions towards that. There's not too much more left, and I just wanted your opinion on whether you think that's the case.
No, I think it's one of these things. It's not a lot of work. It's 5%, and it's the hardest 5% compared to the other 95. I think it's one of those. No, there really isn't a lot of stuff to do in principle. So things like taking duration into account and making sure that people know what the units are, because some people know, but most people don't, such that you can stick in a phantom and do a calibration, and this is what's going to come out. Those and decay, putting that into the normalization is one of these things that I'm sure Daniel is on his list for a long time, and now says, "Oh, I really should have done it." But and same to me. So these things are really quite small. I think the big thing in quantification well, there are two big things. One is dead time, and then you get into really knowing what your scanner does and being able to model that. And that just becomes, I mean, I know it for some scanners, but certainly not for all. It becomes quite painful. And so with PetCert, our intention is to shift that responsibility to the manufacturers, to the converter, essentially. So we, as opposed to saying, give us the information such that we can compute that time factors. That turned out to be very hard because different vendors have very different ways, very different things that they measure and that they then compute the dead time from. That's very hard. So we've decided to say, no, the converter needs to, in some fashion, give you the dead time factors. Not completely, but anyway, that's too much detail for now. So once this is, they agree, they've agreed in principle, but obviously not yet in practice, that this will happen. Then putting that time corrections into our reconstruction will be really easy. Yes, but until that happens, you can do it for one scanner, but doing it for many different scanners is going to be very painful. It's just very, very varied. And that the final thing then is that if you say I have quantitative software, well, then you need to test it. And in some sense, it's quite interesting to see that the Spect people are way behind in quantification compared to PET. But for STIR, that's an advantage because if you tell to Spect people, I'm sorry, you need to stick in your calibration scan and you need to measure it, you need to reconstruct it with our software, you need to find your calibration factor. They say, yeah, of course, I'll do it. If you say that to a PET person, they say, no, I don't want to do it, but because my scanner does it already for me. Right. Yeah, because the vendor has made it so easy for us, we then try to say, okay, we try and see what does the vendor do and then try and reproduce it in STIR. So again, PetCert will make all of that much easier. How long it will take us to get all of that stuff sorted, I'm not sure. Our timelines for the project are saying, okay, the vendors should be starting writing converters in roughly a year's time. If they will and what quality they will be, we'll see.
Yeah, it looks good. I have many more questions and a conversation I would happily have with you, but I'm going to let it. Does anyone else want to ask questions?